Dear students, this is Anu. Welcome to yet another online tutorial on principles of communication system. So now we are into module 4 and this is the fifth video of this particular module. And so far we have seen the need for digitization, right? The very basics of sampling, right? Ideal sampling process, we have mathematically modeled it, right? We even found out the spectrum of a sample signal, right? From the knowledge of spectrum we like understood how the original signal can be reconstructed from the known samples, right? And thus we derived the sync interpolation formula for reconstruction, right? So that's what we have seen so far. So now that we are comfortable with the sampling process, right? So in this session we'll start with the very basic form of actually what analog pulse modulation, that is pulse amplitude modulation. So before we move ahead and discuss pulse amplitude modulation, so I would like to discuss some of the practical aspects, right, which has to be considered while we are sampling a signal. So we told the sampling frequency fs should be greater than or equal to twice the maximum frequency content in the original message, which is to be sampled, right? So the Nyquist rate is fs is equal to 2w. So there, right, it's actually called Nyquist sampling rate, or right, and if fs is less than 2w, we'll call it undersampling, and it will cause aliasing, and we may not be able to design a suitable reconstructing filter to get back the original message signal, right? And if fs is greater than 2w, right, normally we call it actually what oversampling, that it's well and good, right? So it's easy. If it is oversampling, it's easy for us to design reconstruction filter, right? So in practically when we are performing sampling, when we are converting an analog signal to digital signal or the bit sequences, right, normally what we'll do is we use a pre-aliasing filter, that is a low pass filter which will restrict the frequency content of the signal to be sampled to maximum w hertz, right? So that if there is any frequency content above w hertz, which mostly will be insignificant, if it is there, that will be removed, so that when we are sampling, right, that aliasing won't be there, or right. And also to make sure there is no aliasing and reliable reconstruction is possible, the sampling rate will keep slightly greater than the Nyquist rate, right? So those are the two practical considerations while we are performing sampling. It's not always fs is equal to 2w. Why I told this is, yesterday when we discussed the sync interpolation formula for reconstruction, at the end I have considered fs is equal to 2w and have written the expression, right? It's not the case. That's actually what the limiting case. Normally fs will be greater than 2w. Please do keep that in mind. So with that note, we'll move on to pulse amplitude modulation. So it's right, as I told initially itself, digital modulation techniques can broadly be divided into digital baseband technique and digital band pass techniques, right? So digital baseband technique is used for wired transmission of signals, right? So mostly we'll be using some pulses, right, to transmit the digital information, right? If it is digital band pass, right, so these pulses will be modulating a high frequency RF carrier, right, and we'll be using it to transmit wirelessly, right? So that is digital band pass. So digital band pass modulation technique, and you won't study anything in this particular semester. You'll be studying that in sixth semester, right? So in this particular module, we'll be studying about the simplest and the most basic form of analog pulse modulation, that is digital baseband modulation, that is pulse amplitude modulation, right? So as the name suggests, in pulse amplitude modulation, the amplitude of a regularly spaced pulses are varied in proportion to the corresponding sample values of a continuous message signal, right? So when I say pulse, it need not always be rectangular pulse. It can be rectangular or some other appropriate pulse shape. It can even be a sync pulse or raised cosine pulse or whatever, right? So, but for our discussion, we'll be considering rectangular pulses. So just now I gave you the definition. I'm sure you may not have got an idea. So we see a simple example of PAM, right? So consider this is our M of t. This is our message signal. If I have to um, modulate it using PAM, what basically it does is actually it involves two steps, right? Initially, we have to, maybe I'll use some other color ink so that right? We'll be able to differentiate it, right? So I'll use this particular ink, right? So this is 0, this is say TS, 2 TS, 3 TS, right? These are the sampling instances, right? These are the sampling instances. Now, this pulse amplitude modulation basically, right, involves sampling, right, to obtain the instantaneous sampled value, right. Then we have to basically lengthen the duration of each sample, right. So pulse amplitude modulation is this, right. So that's what our periodic rectangular pulses will be there, and its amplitude will be scaled by the instantaneous sample values at that corresponding instance. So this is what is called pulse amplitude modulation. So I'm just drawing it here, right? So you can see, right? Maybe I would like to what uh, I would like you to differentiate this from the ideal or I instantly this from the natural sampling. I'll just tell you what is natural sampling. So this is what is pulse amplitude modulation. What you have to keep in mind is the top of each pulse is actually what flat. So the signal which is shown in green, that is our M of t. Signal which is shown, that is our M of t, and the signal which is shown in this red color, that is our. So I'll call the sample pulse amplitude modulated signal as S of t, and you can see this is time instant 0, and this is time instance Ts, 2 Ts, so on and so forth. So the separation between two adjacent uh, pulses, right, or the rising edge of two adjacent pulses will be Ts, and you have to also note the width of each pulse, right? Width of each pulse we are representing it as T. So this is basically pulse amplitude modulation. So the amplitude of regularly spaced pulse trains are varied in proportion to the corresponding sample values of a continuous message signal. So you have to differentiate this between the natural sampling process. Basically, natural sampling, it's actually what most easiest way of obtaining, right, rectangular windowed samples of message signal. So uh, in practice, how we can implement this, if you have a say a, a transistor, right? If you have a say a NPN transistor is there, right? So you'll be giving, right, the rectangular pulse to the base, right, which will basically be sampling this signal, and the message to be sampled will be given to the say collector, right, and if you ground the emitter, what happens is, right, so if this is a NPN transistor during positive half cycle, right, when this M of t, say I'll call it actually what, the pulse, right, so when this pulse, I'll call it H of t maybe, right, when this H of t is positive, what will happen is this transistor basically will be on, or it will be driven to saturation. So what happens is this one will be pulled down, it will be actually what, grounded. So this is the output, right? So when basically when this transistor is on, the output will be 0, and when this during the other half cycle, this transistor will be basically off, right? At that time, whatever is given to this collector, that will be available at the output, right? So basically it will, right, maybe if I'm drawing that, I just want you to differentiate between pulse amplitude modulation. Pulse amplitude modulation, it is also called actually what, sample and hold or flat top sampling, right? So in digital circuitry, this pulse amplitude modulation circuit is actually called sample and hold circuit, right? Or flat top sampling, right? I want you to differentiate PAM and this natural sampling, what I just mentioned now, right? Natural sampling, right? If I draw the waveform, I think you'll be able to appreciate it in a better way, right? Same signal I'll consider. We'll see what happens if you do perform natural sampling on this particular signal, right? Then you will be able to differentiate. I'll take another color. Yeah. Right. So basically in natural sampling, what happened is message signal is multiplied by a periodic train of rectangular pulses, right? So that's this is how you can basically implement that, right? Rectangular pulses. The top of each, say, modulated rectangular pulse varies with the message signal. So that's why, right, when you'll be the top will be varying along with the message signal, right? The top of the pulse need not be actually what, not it's not need not be, it will not be actually uh, flat, right? So that is natural sampling. So the difference between natural sampling, naturally sampled signal, and PAM signal is, in PAM signal, top will be actually what, flat, and in natural sampled, you can see the top of the pulse, it follows the message signal at that, but during that, at that duration. So that's how we can differentiate, right? So basically this PAM or generation of PM, it involves two operations, right? So first one is, right, instantaneous sampling. So I'll first one is instantaneous sampling. So when I say instantaneous sampling, you will be sampling the signal at a rate fs greater than or equal to 2w. So fs or 1 by ts, right? It is greater than or equal to 2w according to our sampling theorem, right? We choose the sampling rate depending upon the maximum frequency content of the signal to be sampled, right? We'll be doing it according to the sampling theorem. So we'll get instantaneous sample, right? So that is the first step. And in second step, we need to lengthen the duration of each sample. So maybe I'll write it as lengthening duration of each sample, right? So that is the second step. So instantaneous sample, we sample, right? So we'll get the instantaneous value of the signal at that particular instance. That is the first step. And in second step, we'll lengthen it to some duration t, right? We lengthen it to some duration t. Then again next sample, right, lengthen it to some duration t. So that those are the two steps involved in our uh, PAM signal generation. So now a question may arise: why do we need to lengthen this? Why can't we keep it a very short pulse? Right? If it is a very short, if we are using a very short duration pulse for natural sampling, or the top will almost be like a constant. Why? Because at that time, much amplitude variation won't be there. Right? Why can't we do that? That can be a question. So the reason is, right, if you reduce the width of a pulse, right, pulse width, if you reduce, what happens is the bandwidth becomes more. So in order to reduce the bandwidth requirement, right, we are extending the right, duration of this pulse to t seconds. So what should be this t, right? What should be this t? That is a question. For that, we need to do some mathematical analysis. So basically, this pulse amplitude modulation, it's instantaneous sampling and lengthening of the duration. So these two operations together, we can call actually what? Sample and hold. Sample and hold, or a flat top sampling, or whatever. Right now, if we need to know, if we should make comments on what should be this t, right? What should be the width of each pulse, right? All those aspects are how can we reconstruct the original signal from PAM signals. For all those aspects, we have to do some mathematical analysis. We should obtain its spectrum, right? By analyzing spectrum, as we have seen, right, after we sampled, what we did is we represented it in the mathematical expression in time domain. Then we obtained the frequency, uh, domain expression for that, or we obtained the spectrum of that. By inspecting the spectrum, right, we could easily decide how we can reconstruct. Right, similarly here also we'll try and do the same process, so that the spectrum, at least let's hope, will give us a way or an idea to reconstruct the signal, right? So that's what some mathematical analysis what we'll be doing now, right? So to, right, So mathematical analysis of PAM. Right. So please do keep in mind. So as per your syllabus, you don't have any actually what discrete component implementation of a PAM system, right? But instead, right, we'll be coming up with a model of an LTI system, or else the impulse response of an LTI system, right? If you can implement in practice, it will give you a PAM system. The syllabus as such does not have any discrete component implementation. So please do keep that in mind, right? So once again, maybe I'll consider a message signal, right? I'll consider a message signal M of t, right? So if flat top sampling means again, yeah, flat top sampling means sample and hold, right? And hold, sample and hold, right? So this is how the PAM signal will look like. Right. So how can we represent it mathematically? That is the question. So this is our, as I told, this is our M of t. Green one is our M of t. Right. So separation between the samples will be Ts, and width of each pulse is capital T. Right. So in that case, we can represent the PAM signal S of t, small s of t, as, right. So summation n from minus infinity to infinity m of nts. This m of nts is nothing but what? Value of m of t at time instance nts, right? So n spans from minus infinity to infinity times h of t minus nts, right? So this h of t, it is actually what? A basic pulse, right? A pulse, right? That pulse is being shifted to every nts, and the magnitude amplitude of that is scaled by the instantaneous, right, sampled value as per, depending upon the definition. I have written this mathematical expression. It's quite straightforward, and we have seen it before itself. So this, now we should see what should be this h of t, right? This h of t, right, it's a regular pulse, right? H of t is a regular pulse. So we'll see this h of t. I'll draw it here. Right, this h of t should be something like this, right? It should span from 0 to t, and during that period its magnitude should be equal to 1. So this is our h of t. So if I define it perfectly, h of t has to be, right, it has to be 1 from 0 less than t less than capital T. And now the question will come, what is the value of h of t at time t, time instance 0 and time instance t? So maybe I can tell it is half at at time t equal to 0 and time t equal to capital T, and it will be 0 elsewhere. It will be 0 elsewhere. So this is our h of t, right? So now h of t minus nts means you will be shifting it by an amount nts. So which is, right, if it's the rising edge is now what, actually what, 0, the rising edge of h of t minus nts will be at t is equal to nts. That is what basically, right, shift, how we'll shift a part. So this is our s of t. Right, now we have, following the definition intuitively, we have written this mathematical expression, but we actually don't know what is this h of, right? So this h of t and h of t we have intuitively written. Now maybe our idea is to come up with a system model or a mathematical model to generate PAM signal, and also to what, reconstruct original signal from PAM signal, right? So for that, right, maybe I'm, right, again I'm using my intuition, right? So I have my signal m of t, right, and I'm initially, the first step, as I told, it's actually what, sampling, right? So initially I have to sample it, right? Then after sampling, I should pass it through some hold circuit, right? Hold circuit, which will basically lengthen the duration of each sample, right? So m of t, once I sample, I'll get m del of t, right? That is our sample signal. And if I pass this del of t through some circuit. If I call, actually I'll assume the impulse response of that hold system, or the LTI system, which I named as hold, it is h of t, right? So then when I pass this m del of t through this LTI system, I'll get s of t. So this is my assumption. Now we should see we have to see what should be this, right? Whether this system model fits into what we have intuitively uh, found out just now, right? So that's what we are trying to do, right? So basically, if m of t is sampled, we'll get m del of t. We have seen in previous sessions, m del of t, it will be nothing but what, summation n from minus infinity to infinity m of nts times del of t minus n ts. So this is m del of t. Maybe I'll call it equation number one. Right. Now, what will happen if I pass this m del of t through an LTI system with impulse response h of t? The output s of t will be nothing but what, m del of t convolved with h of t. Right. The output will be nothing but what, m del of t convolved with h of t. Right. So, right, so far I don't know what is that h of t. Right, I'm just calling it h of t, but later I'll show that h of t is actually what, the rectangular pulse what we have shown. Right. So, but maybe let's assume we don't know what is that h of t. Right. So now the output s of t, I can write it as s of t is nothing but what, m del of t convolved with h of t. Right. So that is nothing but what. So convolution is nothing but, right. We can find the convolution either as actually what, product in frequency domain and inverse Fourier transform. That is one way. Or else in time domain we can evaluate convolution using a convolution integral. You are already familiar with that. So that is nothing but what, integral minus infinity to infinity, right? M del of tau, right? M del of tau times h of t minus tau d tau. So this is the convolution integral. So now if I okay, this is again r s of t, right? So but I know m del of t is nothing but what, this infinite sum, right? So now I'm going to substitute one in this equation. Maybe I'll call this equation as equation number two, right? I'll substitute it here. So s of t is equal to integral minus infinity to infinity. Instead of m del of t, I can write it as summation n from minus infinity to infinity m of n ts times del of t minus nts. So sorry, it's m del of tau, right? So instead of t, I should be writing tau. So instead of t, right, here instead of t, I should be writing tau, right? That is the meaning, right? If when I write m del of tau, instead of t, I should be writing tau. That's it. So del of tau minus nts times h of t minus tau d tau, right? So now this is our convolution integral, right? So you can see there is a summation and integration. Both are linear operators, so I can interchange, right, their orders. So now what I'm doing is I'm just, right, interchanging the order of summation and integration, right? So then what I'll get is summation n from minus infinity to infinity, and you can see this m of nts, right? This integration is with respect to tau, and m of nts, it doesn't have any tau term. It is actually what, independent of tau, so I can take it out of the integral, right? So I have taken it out of the integral m of nts, right, times integral minus infinity to infinity, right? So now it becomes del of tau minus nts times h of t minus tau d tau, right? So we do have this integral now, right? We do have this integral now. It is actually what, integral of product of del of t, shifted version of del of t, and another signal h of t, right? Whatever, right? So by shifting property of impulse function, you might have studied this. I will just recollect what is that. By shifting property of impulse function, right? So if you have a time domain signal x of t, right, if you integrate the product of x of t and del of t minus t naught, right? This x of t is a signal as such. Del of t minus t naught is nothing but what? Del of t shifted right by some amount t naught, right? Some constant amount t naught. So then this will be equal to x of t naught, right? So this value of this integral, right? As you know, del of t minus t naught, it will be defined only at t equal to t naught, and if you integrate del of t, you will get the area will be equal to unity. So by shifting property, right, if x of t is multiplied with del of t minus t naught, right, it will give you the instantaneous value of x of t at t equal to t naught. So what you should do is this t you should replace with t naught, right? Mathematically, that is what you will be doing, right? So x of t into del of t minus t naught, if you integrate that product from minus infinity to infinity, right, it will be x of t naught. So please see, note down carefully, right? So what we have done is we have replaced the t, right? This integration is with respect to t, right? So this x of t, in x of t, t is replaced with the constant uh, time shift, right? T naught, right? That is shifting property. So you have studied this maybe in signals and system, while you were studying the basic properties of actually what delta function and all, right? So if you apply the same property here, right, you can see here we have del of t minus nt tau. This integration is with respect to tau, right? So we have del of tau minus nta. So this is actually what this is corresponding to our t naught. That is a shift amount of shift, right? And we have another function h of tau, right? H of t minus tau. This t we don't have to bother. Why? Because our integration is with respect to tau, right? So this you don't have to worry about this t now, right? So what you should do is, if you by shifting property, right, this instead of tau you should replace it with actually what? T naught. Tau should be replaced with T naught, right? So that's what we have to do. So by shifting property, I'll be writing that, right? So I'll write now h of t is equal to summation n from minus infinity to infinity. We have m of n ts, right? Then this term will become h of t minus nts. What I should do is I should replace tau with nts. I don't have to bother if anything else is there as an argument of this function h, right? I don't have to bother. So this is, it becomes h of t minus n ts. This becomes h of t minus nts, and right, I'll call it equation number. This is equation number. Right, let me just uh, quickly check. This will be equation number 3, right? But if you compare equation number 1 and equation number 3, both are actually what? So not equation number 2 and equation number 3 or 2. I have written, yeah, this I didn't give any equation name, right? So the first one I'll give equation A, right? If we compare equation A and equation number 3, you see that this h of t should be the rectangular pulse what we have actually what initially assumed, right? Intuitively we have assumed that that pulse should be uh, a unit pulse spanning from 0 to t, right? It will be same. So this is equation number 3, right? So when you compare equation A and 3, when you compare equation A and 3, right, we can maybe infer this PAM signal is mathematically equivalent to what? The convolution of instantaneously. So this M of NTS is nothing but what? Instantaneously sampled version of M of T, right? Or value of M of T at every instance NTS, where N will span from minus infinity to infinity, right? That if that is convolved with uh, the pulse h of t, right? That will give us s of t. Maybe I should write that, right? So the inferences by comparing A and 3, right? Now we can come to a mathematical model, right? So we can come to a mathematical model. So A PAM signal, right, is mathematically equivalent to, that is the inference which you have to draw from these two, right? So this will help us to what come up with the system model, right, or the mathematical model equivalent to the convolution between convolution uh, of, that is m del of t. What is this m del of t? M del of t is nothing but what? It is instantaneously sampled version of m of t, right? Instantaneously sampled version of m of t, right? M del of t is nothing but what? Instantaneously sampled version of m of t, and so a convolution between m del of t and h of t. Where we know what is h of t. H of t is nothing but what? H of t, it's a pulse. It spans from 0 to t. Right. This is a h of t. Right. This is a h of t. So I can now draw the system model. Right. So initially this m of t, it should be sampled. Right. It should be sampled. Right. It should be instantaneously sampled, and the sample signal should be passed through an LTI system with impulse response h of t. So what I'll get here is m del of t, and the output of this h of t should be equal to s of t, right? So I can write s of t is equal to m del of t convolved with h of t, or if I take Fourier transform of this, right? So convolution in time domain, it becomes actually what? Multiplication in frequency domain. So if I take Fourier transform of this, I'll get s of f is equal to m del of f times h of f, right? So where s of f will be actually what? Fourier transform of s of t, that is our PAM signal. M del of f is nothing but what? Fourier transform of m del of t, and h of f is nothing but Fourier transform of h of t, right? Or this is the transfer function of this particular filter, right? So this is what we can infer from this, and we know, right? We have if we know the spectrum of m of t, right? So if the Fourier transform of m of t is m of f, right, and it has a typical baseband spectrum like this, right? If it has a typical I am showing the normalized spectrum, right? I'm showing the normalized spectrum, which means frequency at maximum frequency is normalized to unity, right? So uh, that's what, right? So if this is our m of f, right? If this is our m of f, right? Then we know m del of f will be fs times summation n from minus infinity to infinity m of f minus n fs, right? So this will be our m del of f. So I'll call it equation number, say, 4, right? To m del of f is that. So, but now the question is, what is this h of f, right? If you know what is h of f, then you can straight away find out what is the uh, spectrum of s of t, right, or s of f, right? So for that, right, maybe we know what is h of t, of course, right? Our h of t is this 0 to t, and magnitude is 1. This is our h of t, right? But we do have a standard result, right? We know the spectrum of a rectangular function, rect of t by capital T, right? Rect of t by capital T, it is Fourier transform pair with t sinc of ft, right? So this is a very basic result which you all may be knowing, right? So the rectangular pulse and sinc function, they are actually they form Fourier transform pair, right? So this rect of t by t, it is nothing but what? A rectangular pulse which spans from minus t by 2 to plus t by 2, right? So this is rect of t by t. Let's say I'll call, if x of t is rect of t by t, then x of f will be, right, x of f will be t sinc of ft. So t sinc of ft, if it's actually what, sinc of ft scaled by a factor t, right? So in yesterday's session, I have in detail discussed, right, what actually is sinc function. So sinc of ft will be what, sine pi ft divided by pi ft. So it will have maxima, right? It will have maxima at f is equal to 0. So at f is equal to 0, it will have maxima, and that will be equal to t, and it will pass through zeros. So how to find out what will be the zeros, for what values of f it will pass through zeros? For that, pi f capital T should be equal to what? Integer multiples of pi. So this pi and pi gets cancelled, right? So f is equal to n by t, right? So for integer multiples of 1 by t, it will pass through 0, right? So 0, right? So I can draw it like this. So this will be, right, if x of t is rect of t by t, so if it is spanning from minus t by 2 to t by 2, right, our x of f will be t sinc of ft. T sinc of ft will have maximum value t at time t equal to 0, right, and it will pass through zeros at time instance 1 by t, 2 by t, so on and so forth, and both on negative and positive frequency axis, right? So this is sinc function. But now this is our x of t, but our h of t is nothing but what? X of t shifted right by an amount t by 2. Right. This h of t is nothing but what? X of t shifted right by an amount t by 2. So maybe I think we can use time shifting property of Fourier transform and find the um, Fourier transform of h of t. Right. So this h of t is nothing but what? This is 0. H of t is nothing but 0 to t. So this I'll write h of t. It is nothing but what, x of t shifted right by an amount t by 2. Right. So then, right, what will be the Fourier transform of this? Right. The by time shifting property, if Fourier transform of x of t, maybe I'll just once again I'll write that. Right. I have initially, as a part of prerequisite in first video, second video itself I've discussed, but once again I'll write, not a problem. Right. So yeah, the time shifting property is of Fourier transformers. If x of t, it's Fourier transformers x of f, right? Then the Fourier transform of x of t minus t naught will be x of f into e power minus j 2 pi f t naught, right? So this is the time shifting property. So if the original signal is delayed or advanced by an amount t naught, right? So the, you can see the magnitude spectrum, it will remain the same, right? So x of f into e power j 2 pi f t naught, it's a complex number, right? And it's in the form actually what, r angle theta, r angle theta, or r e power j theta, right? So this r is a real part, and e power j, whatever be the argument of this e power j, that will be the phase, right? So you can see the magnitude spectrum of x of t and x of t minus t naught, it remains the same, right? It's x of f itself, right? And the phase, you can see it shifted by an amount e power or j 2 pi f t naught. So there is only what, a change in phase, right? So now I can write h of f will be, right, Fourier times h of f will be equal to what, t sinc of ft times e power minus j, right? It will be 2 pi f, instead of t naught I should substitute t by 2, so that by 2 and 2 will get cancelled, so I'll get e power minus j pi f t. So this will be our h of f, right? This will be our h of f. So now I can write the final expression for s of f, right? So this s of f is nothing but what, m del of f times h of f, right? Where this m del of f is nothing but what? Fs times summation n from minus infinity to infinity m of f minus n fs times this h of f is nothing but what? T sync, say, yeah, T sync ft, right? Yeah, T sync ft times e power minus j pi ft. T sync ft times e power minus j pi f t. So this will be our s of f, right? So now, even though it's actually what a very big expression, right? But we can easily actually what visualize this, right? Once we visualize, we'll get an idea. So how the spectrum of this PAM signal is related to the spectrum of the original message signal m of t, and from that relation we can find out how to reconstruct a signal. So maybe that thing we'll be doing in the next class, that is how to visualize this, right? So that unless you are able to what visualize, you won't be able to come up with a solution for the reconstruction problem, right? So this is actually the spectrum of, I didn't draw the spectrum of uh, this SOFF now, so that spectrum of visualizing the spectrum of SOFF and reconstruction and maybe something called aperture effect and how to overcome that, all those aspects we'll be seeing in the next video. So before I wind up, right? So we have seen what is pulse amplitude modulation, right? And we have differentiated pulse amplitude modulation and the natural sampling process, right? So we intuitively we came up with a mathematical model of pulse amplitude modulation. Then later on we verified, right? We can obtain the pulse amplitude modulated signal by sampling m of t, right? And after the sampled signal, if we pass through an LTA system with impulse response h of t, that is a rectangular impulse response h of t, that is an ideal actually what low pass impulse response. If we pass through that, right, we will get our PAM signal. It's not actually LPF. It's not a double-sided. Okay, fine. Yeah. So we'll get our SOF. So once I draw that, it will be more clear to you, right? So that's what we have done in today's class. We have derived the expression for SOF. Now, in next class, we'll try and plot this, and uh, as a continuation of that, we'll try to come up with the solution for the reconstruction problem. And I, so today I'll wind up the session with this. I thank you so much.